Over the course of the past modules, we've been learning all the things that we can do with Python, from managing files to processing text, starting system processes, and a whole lot more. Up to now, whenever we wrote Python code, either in the interpreter or in our scripts, we've been testing it by manually running it and seeing if it did what we expected it to do. Buckle up, because that's about to change. In this module, we'll dive into how we can create automatic tests that will perform these kinds of checks for us. This lets us concentrate on just writing the code instead of checking if any changes that we make to it break the previous functionality. It would also help us verify that features we add do what we expect in lots of possible ways. We'll learn about the different kinds of testing that are out there and how we can use them to make our code more reliable. And finally, we'll also learn about how to handle errors and exceptions in Python code, how to trap those errors so they don't stop our programs from completing, how to raise errors when necessary, and how to test our code generates the right kinds of errors. That sounds interesting, right? Now, let's get to it. When you're writing a very simple piece of code, say for example that you're adding two variables, it's pretty straightforward to know what the code does and be sure that it does it correctly. As the operations become more complex, using loops, conditionals, calling more and more functions, it's harder to really be confident that the code will do what it's supposed to. This is where software testing comes into play. Software testing is a process of evaluating computer code to determine whether or not it does what you expect it to do. When you test a piece of software, you want to find the errors and defects and see where things go wrong. Software testing is similar in lots of ways to the tests performed in the manufacturing process of a new piece of machinery. When a new car comes off the line, you want to make sure that when you press the gas, the car will go, and when you press the brakes, the car will stop. It's the same idea with software. You want to make sure that when you run a program, it behaves the way that it should. Then you can really put the pedal to the metal. Vroom vroom. Scripts and programs can fail in all sorts of strange ways, especially as they become more and more complicated. In all but the most simple programs, it's next to impossible to test for everything that could go wrong. Even though this means that a certain number of bugs might exist in your scripts without you realizing it, don't worry. Writing tests can help you eliminate a whole bunch of bugs, helping to improve the reliability and the quality of automation. Tests can help make good code great. The field of software testing is pretty broad. In the next few videos, we'll explore some fundamental concepts involved like automated testing, unit tests, integration tests, and test-driven development. As with lots of topics covered in this course, we'll do a quick rundown of the many concepts around testing. It won't be enough instruction for you to become a testing expert, but it should help you with automatically testing your scripts. Up next, we'll talk about the differences between manual and automated testing. So, let's shift gears and get started. One of the tasks that programmers have to do when writing code is test it to make sure that it behaves the way that they expect it to. Having good tests for our software can help us catch mistakes, errors, and bugs before we deploy our scripts to perform real-world automation tasks. The most basic way of testing a script is to run it with different parameters and see if it returns the expected values. We've done this kind of manual testing for some of the code that we've written in this course already. Executing a script with different command line arguments to see how its behavior changed is an example of manual testing. Using the interpreter to try our code before putting it in a script is another form of manual testing. Formal software testing takes this process a step further, codifying tests into its own software and code that can be run to verify that our programs do what we expect them to do. This is called automatic testing. The goal of automatic testing is to automate the process of checking if the returned value matches the expectations. Instead of us humans running a function over and over with different parameters and checking that the results are what we expected them to be, we let the computer do this for us. Automatic testing means we'll write code to do the test. Why would you write more code to test the code you have? Because when you're testing your code, you want to check if it does what it's supposed to do for a lot of different values. You want to verify that it behaves the way you expect it to with as many possible values, known as test cases. Say you're writing a script that updates a list of email addresses to use a new domain, similar to the one we wrote a while back. You'll want to test what happens when your list of emails has 1 element, 2 elements, or 10 elements. You'll want to test what happens if the new domain is 1 character long or 20 characters long, or even an empty string. You'll also want to test what happens if the list contains only emails that need to be updated, only emails that don't need to be updated, or a mix of them. As you can see, the list of things that you want to test for can get very long very fast. The more test cases that you include in your test, the better tested your code is, and the more you can guarantee that your code does what you expect it to do. If we're testing this manually, it's unlikely that we'll go through all the cases whenever we change our code. We'll test just a few, possibly letting a bug slip through. Not ideal. This is why we don't want to perform these tests manually, and instead, we want to make our computer do it for us. Just like with any example of automation, the advantage of automatic tests is that we can run them as many times as necessary and will always get the same results. The computer will do the same checks over and over and will always make sure that the return value matches our expectation. When, for some reason, the results don't match the expectations, the code will raise an error so that we can check the code and find out what's going on. There's a bunch of different types of tests that we can write to perform automatic testing. The one that we're going to concentrate on in the next few videos is called unit testing. Once we've covered unit testing, we'll talk about other kinds of testing and when to use each. As we mentioned, there are lots of different types of tests that we can write to perform automatic testing. The most common type is a unit test. Unit tests are used to verify that small, isolated parts of a program are correct. Unit tests are generally written alongside the code to test the behavior of individual pieces, or units, like functions or methods. Unit tests help assure the developer that each piece of code does what it's meant to do. An important characteristic of a unit test is isolation. Unit tests should only test the unit of code they target, the function or method that's being tested. This ensures that any success or failure of the test is caused by the behavior of the unit in question and doesn't result from some external factor, like the network being down or a database server being unresponsive. In other words, when testing a function or method, we want to make sure that we're focusing on checking that the code in that function or method behaves correctly. We don't want our test to fail for external reasons. On a related note, our test should never modify the production environment. This is a live environment that runs the software that users interact with. When developing tests, if for any reason we do need to interact with some other software, we'll normally do that in a test environment, where we'll have control over how it behaves. It's our house, our rules. So, the goal of the unit test is to verify that small, isolated parts of a program are correct. How do we do that? It generally boils down to a simple pattern. Given a known input, does the output of our code match our expectations? Let's take a piece of code similar to what we wrote a while back to rearrange a name in the format last name, comma, first name. And think about how we test it. How do you think we can test that it works the way you expect it to? Let's start by manually validating that for a given input, it produces the expected result. We'll check this by importing the function in an interpreter. To do that, we'll use a keyword that we haven't seen before, from, like this. In this case, rearrange is the name of the module that contains the rearrange name function. By importing it in this way, we can call the function without having to write the module name each time we want to call it, like this. The function has produced the output we expected given the input we provided, and so it has passed this particular unit test. Gold star, hang it on the fridge. The test focused on a small, isolated piece of the code and validated our assumption about how it worked. Because the scope of the test is restricted to a small, specific unit, these types of tests usually run pretty quickly, and debugging them is simple, since there are a limited number of reasons for them to fail. Creating unit tests for our code will mean writing a bunch of test cases that verify that when we input some parameters, we get the output that we want. Of course, the whole point is to run these tests automatically, so that we don't have to manually do this ourselves each time. Up next, we'll talk about how we can actually write automatic tests in Python. Exciting, right? We've now looked at the principles behind automatic testing. We know that by having automatic tests, we can run them as many times as necessary to make sure that our code does what we want it to do. So, how do we do this in Python? We need to write some code that runs the test and verifies the output. This way, we can get our computer to do the work for us. To demonstrate the testing workflow, we'll create unit tests for the rearrange name function from the previous video. As we touched on earlier, automatic tests are usually written alongside the code that we want to test. What this means in practice is creating a separate Python file with the test. The convention is to call this script with the same name of the module that it's testing and appending the suffix _test. So, for our rearrange module, we'll create the rearrange test.py file. We'll test the rearrange name function of the rearrange module. So let's import that function the way we did before in the interpreter. Okay, we're ready to start writing the test. To help us with that, Python provides a module called unit test. Thanks, Python. This module includes a number of classes and methods that let us easily create unit tests for our code. The first thing we'll do is import the unit test module we'll need for testing. The unit test module provides a test case class with a bunch of testing methods ready to use. To access this functionality, we create our own class that inherits from test case, thus inheriting all those testing methods. So we're going to write our own test rearrange class that inherits from test case. Do you remember what the syntax for that was? We need to include the class that we want to inherit from in the parentheses. We've called our test class test rearrange and indicated that it should inherit functionality from the test case class located in the unit test module. Any methods we define in our test rearrange class that start with the prefix test will automatically become tests that can be run by the testing framework. So, we're ready to write our first test case. What's it going to be? In our last video, we manually tested one simple case. Let's turn that manual test into an automatic test that verifies the basic names are formatted correctly. With this method, which we've called test_basic, we kick off by setting up our expected inputs and outputs. We then use the assert_equal method provided to us by the test case class we inherited from to verify that what we expected is exactly what we got. The assert_equal method basically says both of my arguments are equal. If that statement's true, then the test passes. If it's false, the test fails and an error is printed to the screen when the test is run. Okay. We've got our first unit test. So, how can we run it? In the main part of our program, we'll call the unit test.main function, which will run the test for us. All right, we're ready to run the test. We'll do that by executing the file that we just created. Let's make our script executable and then run it. Looks good. The output is pretty descriptive, printing out some information about how long our group of tests, or test suite, took to run, as well as the number of tests and whether or not they passed. Just like that, we've tested our first function. It's pretty cool, right? I know there was a lot going on here. If the code is confusing, complex, or didn't really sink in yet, that's okay. Take the time to practice on your own and review the content until it feels natural. Coming up, we'll test even more cases. By now, we know how to write automatic tests in Python. Our test suite includes only one test case though. We need to make it grow. Choosing test cases can be an exercise in creativity. Coming up with different ways a piece of code might break can actually be super fun. We'll usually test that our code works in the general case. But we should also see what happens when we give it some input that we may not expect it to run into under normal operations. For example, what would happen in our function if we gave it an empty string? Let's add a test for that and see. In this case, we're testing for an empty input string. We're saying that we expect our function to return an empty string when it receives an empty string. We check this behavior by using the assert equal function. All right, let's run this. Oh look, our test failed. We caught a problem with our code. Let's take a closer look at the information that the failure gives us. After all, that's what errors are for, right? This error tells us that the test called testEmpty failed, and we see that it failed with a type error, saying that none is not subscriptable. Interesting, we've just discovered an edge case. Edge cases are inputs to our code that produce unexpected results, and are found at the extreme ends of the ranges of input we imagine our programs will typically work with. Edge cases usually need special handling in scripts in order for the code to continue to behave correctly. In our rearranging example, we can handle this edge case by performing a simple check of the result variable before operating with it. With this change, if we use our function with normal input, we'll still get a result that we got before. If we try to use an empty string, we'll catch it with our check and return the original empty string instead. Whether or not we handle this kind of error depends on how we want the scripts to behave. In our specific case, returning the original value makes sense when we can rearrange it. But sometimes, you might actually want your program to crash with an error rather than to go on as if nothing happened. Remember that it's bad for automation to fail silently. Other kinds of edge cases usually include things like passing 0 to a function that expects a number, or negative numbers, or extremely large numbers. These types of conditions are good to consider when writing your test, since they can cause your code to crash or behave in unexpected ways. Sometimes it pays to be a pessimist. You can see how it might require some creativity to come up with these examples. The upside is that when writing automatic tests, once you've come up with an example, it's there to stay. So, now that we've fixed our code to behave correctly with this edge case, let's run our test suite again and see if the problem is fixed. Yes, our tests pass. We fixed a bug in our code, and by adding an automatic test, we can make sure that it won't happen again. Up to now, we've added a basic case and an edge case to our test suite. When we added the edge case, it caused our function to generate an error because we didn't handle this correctly. And so we fixed it by changing our function. Can you think of some more examples that will make our function misbehave? Remember, when we first wrote the function, we came across names with spaces or dots that will make our regular expression not match. We fixed that already, but it's still a good idea to add a test case to make sure that our code still works how we expect it to. In this case, we're testing that someone with more than one given name still gets their name properly rearranged. Let's run our test suite and see if it passes or not. Alright, we now have 3 tests and all of them pass. To find more bugs, we need to exercise our creative muscles and think of other examples that might cause our code to fail. How about someone who has only one name? In this case, this person only has one name, so there's no comma in our string. We expect the result to be the same name we provided to the function. Will that work? Let's check and find out. Whoops, this one failed. Bad news for Voltaire. The test output in this case looks slightly different than before. It shows the name of the test that failed, which is test1 name. But now, instead of giving us a type error, we see an assertion error, which means the original and expected values don't match. It looks like our function returned an empty string instead of the original name. That's because there's a bug in our code. And what do we do when we have a bug in our code? We squash it. When we checked if the result was none, we returned an empty string, which made our previous test pass. What's happening now is that we're passing a name that doesn't include a comma, which makes our result variable none, and so the function is returning an empty string. The fix for this is pretty simple. Instead of returning an empty string when the result is none, we'll return the original name variable. So that should be enough, right? Let's save our changes and run the test suite again. Bingo! We fixed all the bugs and all our tests pass. One of the great things about running tests in a suite like this is that we now know that all the test cases we wrote were handled correctly. Our code works for basic names, empty strings, double names, and single names. If we found another case that made our test break, we could add it to the suite, fix the bug, and then run the whole suite again, being assured that all the other cases are still working. You should take a moment and reflect on what you've already learned in this module. It's super impressive, and it's going to fit nicely into your IT toolkit. There are lots of different tests that we can use to make sure our software is behaving how we expect it to. We've explored unit tests in detail, which are both simple to write and a very powerful way to catch bugs. But there's a lot more to software testing. One interesting concept is whether our test is a white box test or a black box test. White box testing, also sometimes called clear box or transparent testing, relies on the test creator's knowledge of the software being tested to construct the test cases. With a white box test, the test creator knows how the code works and can write test cases that use the understanding to make sure that everything is performing the way it's expected to. On the other hand, in black box testing, the software being tested is treated like an opaque box. In other words, the tester doesn't know the internals of how the software works. Black box tests are written with an awareness of what the program is supposed to do, its requirements or specifications, but not how it does it. For example, a simple black box test could be to verify that when you type www.google.de in your browser, the Google search page for Germany is returned. You might not know how Google servers process your request, but you know what the end result should be. Both white box and black box tests have their own advantages. White box tests are helpful because the test writer can use their knowledge of the source code to create tests that cover most of the ways that the program behaves. Black box tests are useful because they don't rely on the knowledge of how the system works. This means their test cases are less likely to be biased by the code. They usually cover situations not anticipated by the programmer who originally wrote the script. Not all tests that we write need to fall into one category or the other. We can write unit tests that are either white or black box, depending on which testing methodology is chosen. If the unit tests are created before any code is written, based on specifications of what the code is supposed to do, they can be considered black box unit tests. If unit tests are written alongside or after the code has been developed, the test cases are made with a knowledge of how the software works. They are white box tests. One way isn't strictly better than the other, since each gives you a different path to make your code more reliable. Not everything is so black and white, or as we'd say in the coding world, binary. As an IT specialist, you might need to test that software written by others behaves the way you expect it to. To do this, you can use a combination of black box and white box test. Let's say that you have an online catalog of products that are sold by your company. You could have a black box test that verifies that the details for a product are displayed when you open the page for a specific product. Apart from that, you could have white box tests that calls the different functions used by that page, checking that the prices are displayed in the right currency, that the description is correctly wrapped, and so on. Next up, we'll talk about other kinds of testing beyond unit tests and what roles they play in improving the quality and reliability of your scripts. When we looked at unit tests, we called out that they should focus on one specific unit, a function or method, that's being tested. This allows the test to verify that the unit provides the expected functionality regardless of the rest of the environment. On the other hand, integration tests verify that the interactions between the different pieces of code in integrated environments are working the way we expect them to. While unit tests shouldn't cross boundaries to do things like make a network request or integrate with an API or database, the goal of an integration test is to verify these kinds of interactions and make sure the whole system works how you expect it to. Integration tests usually take the individual modules of code that unit tests verify, then combine them into a group to test. Depending on what our program does and how it interacts with the rest of the systems involved, we might need to create a separate test environment for our test, which runs a test version of the software that we're trying to verify. We might be able to run our tests against the actual version of our system that's running, but that's only if our code doesn't make any changes to the production environment. Whenever your company is deploying a system that's somewhat complex, having integration tests will help make sure that all the pieces come together the way you expect them to. These tests usually take a bit more work to set up because you'll need to make sure that you have the test versions of all relevant systems. But they might help catch issues that unit tests won't detect, so the extra effort is definitely worth it. For example, if the service you're trying to test interacts with a database, you'll want to set up a separate test database with a test user and test tables. This lets you run all tests you need in an environment that you can control without risking modifying the production database. A variant of unit tests are regression tests. They're usually written as part of a debugging and troubleshooting process to verify that an issue or error has been fixed once it's been identified. Say our script has a bug and we're trying to fix it. A good approach to doing this would be to first write a test that fails by triggering the buggy behavior, then fix the bug so that the test passes. Regression tests are a useful part of a test suite because they ensure that the same mistake doesn't happen twice. The same bug can't be reintroduced into the code because introducing it will cause a regression test to fail. Smoke tests, sometimes called build verification tests, get their name from a concept that comes from testing hardware equipment. Plug in the given piece of hardware and see if smoke starts coming out of it. When writing software, smoke tests serve as a kind of sanity check to find major bugs in a program. Smoke tests answer basic questions like, does the program run? These tests are usually run before more refined testing takes place, since if the software fails the smoke test, you can be pretty sure none of the other tests will pass either. As they say, where there's smoke, there's fire. For a web service, a smoke test will be to check if there's a service running on the corresponding port. For an automation script, the smoke test will be to run it manually with some basic input and check that the script finishes successfully. Other types of tests are load tests. These tests verify that the system behaves well when it's under significant load. To actually perform these tests, we'll need to generate traffic to our application simulating typical usage of the service. These tests can be super helpful when deploying new versions of our applications to verify that performance doesn't degrade. For example, we might want to measure the response time of our website while there are 100 requests per second on our pages, or 1,000, or 10,000. The actual numbers will depend on the expectations of how much traffic our website will receive. Taken together, a group of tests of one or many kinds is commonly referred to as a test suite. A good diversity of test types can create a more robust test suite that helps ensure your scripts and automation do what you tell them to. There are many more kinds of tests out there. We've only touched on a few of the most common types. If you're interested in learning more about the ways software can break and how to test for that, all kinds of books and articles have been written on the subject. Speaking of tests, we have a huge and difficult test coming up. Just kidding. Up next, we'll learn about a technique called test-driven development. You might expect that most testing happens after the code has been written. This seems like a natural progression. First, you write your script, then you write tests that verify that the script does what you want it to do. But this isn't always the best approach. A process called test-driven development, or TDD, calls for creating the test before writing the code. This might seem a bit counterintuitive, but it can make for more thoughtful, well-written programs. When presented with a new problem that can be solved by automation, your gut instinct might be to fire up your code editor and start writing. But creating some tests first makes sure that you've thought about the problem that you're trying to solve and some of the different approaches that you might use to accomplish it. Writing the test first also helps you think about the ways your program could fail and break, which can lead to some valuable insights and even change the approach you take for the better. The test-driven development cycle typically involves first writing a test, then running it to make sure it fails. After all, you haven't written the code to make it pass yet. Once you've verified it fails, you write the code that will satisfy the test, then run the test again. If it passes, you can continue on to the next part of your program. If it fails, you debug and run the test again. The cycle is repeated for each new feature of your script until it's up and running. So, before you write your next Python program, you might want to think about the kinds of tests you can create to make sure it's working as you expect. There are all kinds of resources out there if you'd like to learn more about how you can create code using the test-driven development approach. Lots of them are Python-centric, but the principles can be applied to any language you need to create in. Hopefully, you can see the benefits of writing tests to validate the code you write, and you've gained some understanding about the different testing techniques available. Remember that good tests help make any automation and scripts you write more robust, resilient, and less buggy. Having reliable automation makes life better for everyone. Many companies take testing a step further and combine it with their version control systems and development processes. When engineers submit their code, it's integrated into the main repository and tests are automatically run against it to spot bugs and errors in a process called continuous integration. Although useful, setting up a continuous integration process can be a big undertaking. We'll talk more about it in a later course. In the meantime, if you use unit tests to validate the code you write, you're already on your way to a more reliable and robust automation. Along our journey learning Python, we've encountered errors generated by the interpreter a bunch of times. We've seen examples of type error, index error, value error, and others. Up to now, whenever the interpreter threw one of these at us, we changed our code to avoid the error. That's a common approach, since whenever the interpreter raises one of these errors, the program stops. And we don't want our scripts to come to an end before they're done doing their work. Sometimes it's easy to make a verification with the conditional to avoid the error, like in our earlier example of the rearrange name function where we checked if the result from our regular expression search was none and did something different in that case. Other times, there are so many things that could go wrong that checking for all of them becomes challenging. Say you had a function that opened a file and did some processing on it. What if the file doesn't exist? What if the user doesn't have permissions to read the file? Or what if the file is locked by a different process and can't be opened right now? We could check all of these conditions, but what if there's yet another thing that could cause the open function to raise an error? In a case like this, a better approach is to use the try except construct. Let's look at how it works in an example. Our character frequency function here reads the contents of a file to count the frequency of each character in them. To do that, the first step is to open the file. In this example, we've put the call to the open function inside a try except block. What this does is first try to do the operation that we want, which in this case is to open the file. If there's an error, it then goes into the except part of the block that matches the error and does whatever cleanup is necessary. Here, we have only one except block for the OS error type, but there could be more blocks if the functions called could raise other types of errors. So, when writing a try except block, the important thing to remember is that the code in the except block is only executed if one of the instructions in the try block raise an error of the matching type. In this case, in the except block, we're returning none to indicate to the calling code that the function wasn't able to do what was requested of it. Returning none when something fails is a common pattern, but not the only one. We could also decide to set a variable to some base value, like 0 for numbers, empty string for strings, empty list for lists, and so on. It all depends on what our function does and what we need to get that work done. The important point is that when we have an operation that might raise an error, we want to handle that failure gracefully by using the try except block. The operation could be opening a file, converting a value to a different format, executing a system command, sending data over the network, or any other action that might fail and isn't trivial to check with a conditional. To use a try except block, we need to be aware of the errors that functions that we're calling might raise. This information is usually part of the documentation of the functions. Once we know this, we can put the operations that might raise errors as part of the try block and the actions to take when errors are raised as part of the corresponding except block. You're probably asking yourself, how do I raise my own errors? Lucky for you, that's up next. We'll dive into how to raise our own errors when necessary. In the last video, we looked into how to handle errors when they're raised by the functions that we call. In some cases, we might want to raise an error ourselves. This usually happens when some of the conditions necessary for our function to do its job properly aren't met, and returning none, or some other base value isn't good enough. Let's look at this through an example. Say we had a function that verifies whether a chosen username is valid. One of the checks this function does is verify that the provided name is at least a certain amount of characters, with the minimum value received by a parameter. Something like this. In this function, we're first checking that the username variable has at least min-leng characters. After checking that, we verify if there are any non-alphanumeric characters in the string, which is another criteria for validating a username. If all the checks pass, we return true to indicate that the username chosen is valid. This code works as long as the provided values are sensible. What would happen if the min-leng variable is 0 or a negative number? Our function will allow an empty username as valid, which doesn't make much sense. To prevent this from happening, we can add an extra check to our function, which will verify the received parameters are sane. In this case, returning false would be misleading, because it's not necessarily that the username is invalid, but the provided min-leng value doesn't make sense. So, Let's add a check to verify that minlen is at least 1 and raise an error if that's not the case. Cool. As you can see, the keyword to generate an error in Python is raise. We can raise a bunch of different errors that come already pre-built with Python, or we can create our own if the standard ones aren't good enough. In this case, we're raising a value error, a type of error that we've come across before to indicate that there was a problem with one of the values of the parameters. Let's save our code and then try it out in the interpreter. Success! We imported our function and called it with an invalid parameter. Our function successfully raised an error, just like we wanted. I bet you didn't expect that there'd be a point where getting an error would mean you're doing things right, huh? Let's also try calling it with valid parameters to see if those work. Okay, that seems to work. What if instead of passing a string, we pass something different as a username to validate? Let's try a few examples. First, let's try a number. Uh-oh. In this case, the Python interpreter raised an error because our code is trying to use the length function and we can't do that with integers. Let's try passing a list, which does have a length function. First, an empty list. Because this list is shorter than the minimum length, our code returned false. Now, let's try it with a list of one element. So in this example, we got a different error because we were trying to use the isAllNum method, which is not available on list. We managed to get 3 different possible results when passing a value that wasn't a string. Depending on how our function is going to be used, this could be okay. It's usually the responsibility of whoever's calling a function to call it with the right parameters. But in some cases, we might want to do this explicitly by checking that we're receiving a value that makes sense to that function. So, let's look at an alternative to the raise keyword that we can use for situations when we want to check that our code behaves the way it should, particularly when we want to avoid situations that should never happen. This is the assert keyword. This keyword tries to verify that a conditional expression is true, and if it's false, it raises an assertion error with the indicated message. Let's add an assertion to our function. We've added an assertion that verifies that the type of the username variable is str, which we know is a name that the interpreter uses for strings. If the function is called with a username parameter that's not a string, an error will be raised with the message we provided. Let's try this out. First, we'll need to close our interpreter and restart it to import the modified module. Alright, let's try calling our function with something that's not a string. Aha! We see that our function now raises an error type assertion error if the first parameter isn't a string. As we've called out, we usually don't need to check the types of our parameters. Depending on what our function does, it might be perfectly okay for it to allow scripts to call it with parameters of different types. Assertions can be super helpful if we're debugging some code that's not behaving the way we expect it to. We can add them at any point where we want to ensure that the variables contain the values and types that they should, or when we think that something that shouldn't happen is happening. Heads up though, assertions will get removed from our code if we ask the interpreter to optimize it to run faster. So, as a rule, we should use raise to check for conditions that we expect to happen during normal execution of our code, and assert to verify situations that aren't expected but that might cause our code to misbehave. By now, we've seen how we can handle errors when the code we call generates them, and how we can raise our own errors when we want our code to signal that something hasn't gone well. This is complex stuff, and it's okay if it takes a little while for it to sink in. As usual, we'll include a cheat sheet and give you plenty of opportunities to practice your newly acquired error handling skills. Up next, we'll look into how we can add tests to verify that our function raises the errors that it needs to raise. In earlier videos, we looked into how we can create unit tests for our functions, for both the basic cases and the edge cases. We called out that we should try to cover lots of different possible cases, to make sure that our function behaves correctly in all of them. With some edge cases, like the negative value of minlen in our earlier example, the expectation is that the function will raise an error, and we want to be able to test that too. So, how do we do that? Well, we use the assert raises method, provided by the unit test module. Let's check this out by adding a couple of test cases to the test suite for our validate user function. This is the existing test suite. As you can see, we've got a few test cases checking that the function is working correctly when it receives sane parameters. We now want to add some other cases for when it receives parameters that don't make sense, like a negative value for minlen or a username that's a list instead of a string. Let's do that now. We can see that the assert raises method works a little bit differently than the assert equal method that we used before. In this case, we need to first pass the error that we expect the function to raise, then the function name, followed by any parameters that need to be passed to that function. Behind the scenes, this method is calling the function that we want to test using the try except block and checking that it does raise the error that we said it would raise. Okay, let's run this test suite and verify that our code works correctly. All clear. With that, you now know how to test your code to verify that it does what it should, and how to test that it raises the right error when that's what you expect.
Congratulations on finishing this lesson in the Google IT Automation with Python certificate. Access the full experience, including job search help, and get the official certificate by clicking the icon or the link in the description. Watch the next lesson in the course by clicking here, and subscribe to our channel for more lessons from upcoming Google Career Certificates.